Hi everyone, thank you all for joining us for today's webinar, How AI is Changing Defect Detection. I'm Kirti from Suchi Systems. I'm going to be your moderator for today's discussion. Before we begin, I'd like to cover a few housekeeping announcements for the webinar attendees. The webinar is being recorded and we'll be able to share a link with you in 24 hours after the event is complete. All participants' lines will be muted just to let you know that we'll have a question and answer and comment section. Anytime during the webinar, if you have any questions for the speaker, you can type them in the Q&A box on the right side of your screen. We have a dedicated Q&A session at the end of the event where we'll take them up for discussion. As part of today's webinar, we'll start off with the evolution of defects and the need for defect detection, which is the very essence of software testing, and the evolution of defects over the years and what it means to software testing, followed by the artificial intelligence in testing in the software testing arena today, where our presenter will walk you through an interesting organization example who has been an early adopter of AI in testing and talk about why data is very important for artificial intelligence and how it can help bring better data artificial intelligence outcomes. And finally, we'll conclude it with a question: artificial intelligence or augmented? I will introduce you the presenter for today's session, Vasudevan Swaminathan. He is the President and Chief Consultant in Suchi Systems. At this time, I'm going to hand the floor over to Vasu. Vasu, it's all yours.
Hey, thank you, Kirti. And good morning, good afternoon to all the attendees, wherever you are, whichever part of the globe you are in, or probably if you are from the UK, it's probably good afternoon, good evening for you. Thank you so much for taking the time to join this webinar today. I know that it's a very important area of emerging technology that everyone is talking about. And Shuchi Systems felt responsible, given that we are working in this space for a considerably long time, which is both artificial intelligence and testing. We felt that we should take the responsibility of explaining what exactly is artificial intelligence doing in the software testing space, and is it actually contributing to defect detection? And are there areas of artificial intelligence that can really work well for software testers? If yes, what kind of skills they would need to enhance themselves to embrace the emerging technology called artificial intelligence and things like that. Now, before I get started with the webinar itself, I just wanted to set a few things for clarity purposes. I'm using the terms fault, bug, defect slightly on a loose basis, or very interchangeably. I know that the International Software Testing Board and experts like James Back have very, very specific definitions of this. So if you're already ISTQB certified tester from India, you might probably put a question in the box saying the moderator or the presenter said bug and fault are same. They are not. I understand. I'm using these terms very, very loosely, so bear with me, because the focus here is to talk about artificial intelligence and its effectiveness, or how it is influencing software testing, rather than getting into the definition of testing terms or testing vocabulary. That's one thing. Secondly, I'm not getting into too much of automation in this. That's not the area that I wanted to talk about today. So I'll be very happy to address any questions that you have, but I'm going to talk more in terms of how really is artificial intelligence, impacting defect prediction and defect detection, and in that sense, what is it doing actually? So that's what I'm going to focus on. So with that being said, I will move on to the first deck of the webinar slide presentation. And I would like to talk about the need for defect detection first. Again, just a note, there may be a little bit of lag when the slides actually change here, so bear with me. I think all the attendees might have some lag, or some of you might have a lag in the presentation when the slides are being changed, so please bear with us. And with that being said, I'll talk about the need for defect detection. The need for defect detection, as most of us know, has multiple reasons. To capture the effectiveness of testing, to know if you are building a quality application and things like that, which is very, very important, needless to say. But I think from an organization standpoint, it is even more important because defects are more expensive to fix, when compared to later when they are found actually. So we have been talking about this for many, many years now. but it still continues to be something that's happening, right? We still have defects, we still find defects in production and things like that. And we continue to talk about how important it is to find defect in the same phase. As a matter of fact, if there are test managers who are attendees in this presentation, I'm pretty sure that you would be collecting a metric called defect containment phase, which something has been practiced for many years now. Are we able to contain defects in the same phase in which they are being found? Are we able to fix them in the same phase in which they are being found? So I think from an organization standpoint, that's a very, very important metric. The simple reason being, when you do not fix a defect in the same phase in which they are found, the exponential value of fixing it becomes very, very higher, both in terms of effort and both in terms of, and in terms of cost. So we have been talking about this for many years now. So if you find a design issue, then it needs to be fixed or identified and fixed in the design phase itself. Just in case if it moves to implementation, there is a 5x, impact in terms of cost and effect. And the same, if it slips past implementation and goes into integration testing, or it slips integration and goes into customer beta test, or eventually it kind of passes through all these phases and ends up in production. So depending upon the phase it slips and where it gets caught, the impact of fixing it both in terms of cost and effort is going to be significantly higher. Now, apart from this, there are also various reasons why you want to find defect, why you want to go for defect detection early. Simple reason is you want to find out the effectiveness of testing, and you want to even look at defect detection percentage as a metrics to find out how much of defects are we detecting even before something is found in different environments. How much of the testing environment is used to find defects when compared to a staging or when compared to a production environment and things like that actually. So that's a very, very important area to understand before we proceed any further, and hence we started off with the need for defect detection. With that being said, let's look at a historical view of what's happening with defects. Ever since software programming become a profession, software programming become a serious habit actually, and also look at the evolution of software testing in that context. Now, when we talk about evolution of defects, there are a lot of defects that are being found in different phases. But there are different types of defects that have actually made an impact across the world. But we are trying to take a few defects here and there and try and talk about some of these in the context of its evolution and how software testing is addressing them actually. Now, we recently just passed the World Testers Day, which was on September 9th. And just in case, if some of you are not aware, the World Testers Day is being celebrated on September 9th because Grace Hopper, one of the early software programmers from the United States, found a bug, literally a bug, on the September 9th, actually, 1947, September 9th. So that's one of the reasons why World Testers Day is being celebrated on the 9th of September. So when Grace was working on the Mark II computer at Harvard University in 1947, her associates discovered a moth that was stuck in a relay, an insect or a bug actually, a literal bug. So the moth kind of impeded the operation of the relay. And while both Hopper or her queue did not mention debugging in their logs, this particular case was held as an instance of literal debugging, actually, which is removing the bug from the relay and making it work. So the origin of the term probably could have come from here, and it's been used in engineering actually for a long, long time now. And in fact, if you are interested, you can check out the remains of the moth at the Smithsonian Institution, which is at the National Museum of American History in Washington, D.C. actually. So the reason I wanted to highlight that is this, it's considered to be sort of the world's first bug. But from there on, if you look at it, there have been a number of bugs actually. So the Mariner 1 spacecraft in 1962, which actually missed a hyphen in the code, leading to a lot of issues. Similarly, Morris Worm in 1988, which actually sort of created a ruckus in the internet, and cost of cleaning up went up to 100 million actually. And the Heathrow Terminal 5 opening in 2008, which was one of the most largest issues that we've seen in recent times in terms of a bug crashing an entire system. So the baggage handling system at Heathrow completely came to a standstill as a result of the bug that they found. And again in 2019, earlier this year, a certain number of bugs were actually causing more than 100 plus flights to be cancelled and more than 200 to be delayed as a result of some signal issues where the bug was found actually. And this happened again with British Airways actually. So It is important to understand the evolution of these defects. The reason being, defects continue to be found, and defects only continue to be found as and more features are being implemented, as and more features are getting added. So, for example, a recent statistic says that in any device, within 18 months, there are a number of softwares that are getting deployed. Like within a span of 18 months in the same device, you can see that a number of software is being deployed. So when you deploy software at that level of speed and agility, it is very natural that you get to find a lot of defects actually. So with that being said, let's try and understand what's the evolution of software testing in terms of addressing these defects actually. Let's look at how software testing has evolved over the years. Now, currently we are talking about cloud and things like that, but where exactly it all started and where we are today. Um, It all started off with the waterfall style of doing software programming, where people were more in terms of manual testing. So, as we all know, waterfall is more like staged or a step-by-step methodology where you start off with requirements, move into software design, do high-level, low-level design, then development, testing, and things like that. So, by the time in a waterfall model, when you start writing code, and by the time the feature comes to testing, no one is going to test intermediately, or apart from unit testing, there is nothing much happening over there. So which means that manual testers who are working on the testing phase there used to find a lot of defects actually, which was the case during late 80s and early 90s. And then sort of automation tools got introduced during the mid 90s, late 90s actually. I'm sure some of you here would have heard about tools like Windrunner, Silk Test, and things like that. So tools like that actually were changing the landscape for testers. And at that point of time, testers were not doing a lot of scripting and things like that, but they were basically trying to mimic the manual actions. And in the process, they were trying to see if automated tests can run for the regression pack. And they were trying to use that to find defects and things like that when the code causes a regression and all that actually. And then as we moved into 2000, that's when the agile storm actually happened, because during the late 90s, if I'm not wrong, in 1999, a team of people who got together at the ski resort in Utah came up with 12 principles of agile, which they published as the Agile Manifesto. And the early 2000 and after that has been a complete agile world basically. So naturally, testing was forced to change its ways in terms of being fit into a sprint model, agile model, and things like that. And at that point of time, when you look at it, it started off with behavior-driven testing, test-driven development, what do you call as Kanban and things like that. Different variants of agile that were used actually, within which testing was actually fitted in. So either people started doing functional testing in the same sprint, and then they started doing regression in the successive sprints, or they started off with automation in sprint one, where they tried to write manual test cases in sprint zero before automating it in sprint one and things like that. So for the most part, since the mid 2000s, late 2000 actually, or I would say from the mid 2010, if you take it 2005 to 2010, there has been a lot of change with respect to testing from an agile standpoint, and it has even more increased and improved as a result of newer variants such as continuous testing, continuous integration, delivery, and things like that. So disciplines have changed over time. So people have found the need to do faster releases, given that it's a very, very agile product release methodology that we have now. Products have to be released faster to the market. So naturally, there is a need to do a lot of push of the button deployment and things like that. So after 2010, it has been mostly in terms of scaling agile methodologies, bringing in disciplines like continuous integration and continuous delivery, where testing again was made into a continuous testing, or was recreated as continuous testing, where people said, you should be able to run test cases continuously, automation scripts have to be run continuously, and things like that. Now, we are in that phase right now, actually, and people are already talking about artificial intelligence as a game changer for software testing. Now, there are some early comments about it. There are companies that are talking about, test automation being completely handled using artificial intelligence. There are companies that talk about test case generation, optimal test cases being identified using machine learning and things like that. Now, again, it's important to understand that artificial intelligence the moment we use this term, we visualize a physical robot, or we try and visualize a software robot, or talk about or think about robotic process automation and things like that. Now, that's one part of, maybe artificial intelligence, but within the gamut of artificial intelligence, the most important part where actually intelligence comes in is in two areas, in two allied areas of artificial intelligence, which I call as, which the industry calls as data sciences and machine learning, basically. So data sciences and machine learning is the place where most of the intelligence comes from. And whether you build a physical robot, or you build a software robot, or you build a chatbot, an interactive chatbot, or you try and do any kind of, prediction accuracy, anything, not necessarily in software testing, in any industry. When you look at all of this, it basically goes back to data sciences and machine learning. And as the terms say, it all goes back to data. So we will discuss more about that, but I generally wanted to give an overview of how the evolution of software testing is happening and where software testing is headed for the future. So when we talk about autonomous testing, machine learning, artificial intelligence as the collaborative, smart testing, intelligent testing for the future, let's look at what is actually happening there. Now, artificial intelligence in testing is not new, but artificial intelligence in software testing is new. So I would like to introduce you to some of the industries which are already using artificial intelligence and show how we can learn from them and apply it in software testing. So for example, in fact, I would like to give a small thing for the attendees here. If the attendees are interested, if you want to go and do a Google search, basically, if you go and use the terms, let's say, use the phrase, let's say, using artificial intelligence for defect detection, try doing this. Open Google and go to the search box and say, using artificial intelligence for defect detection. When you try and do this, you can see that you would hardly get to see any software testing defects, or there will not be any searches that actually come relevant to software testing and defects. Actually, most of the responses that you see will be related to other industries. So that's why I wanted to focus a little bit in terms of how other industries are leveraging artificial intelligence and machine learning today, and what we can learn from them and apply it in software testing. So now, in manufacturing of phones or any manufacturing lines, artificial intelligence and subsets of artificial intelligence like data sciences and machine learning are very much in use. Let's look at an example. Instrumental Incorporated is a company that's based in Silicon Valley, and it was founded by two Apple engineers, actually. Now, this company is trying to use machine learning and deep learning to help defects or faults that are found in production lines, basically. When I say production lines, these companies work with names like Motorola, where large-scale batch processing of mobile phones happen. Now, when a mobile phone chip is wrongly put in, or if there is a defect in the if there is a defect in the chip, it is very difficult to catch it with the human eye. So what this company is making an impact in this space is they are trying to use machine learning and deep learning here. So what they do is they collect the images of all the past errors, past faults that has happened, and then use these images and store it in a cloud database. And from that database, they do a runtime check on the batch processing system to see if there are any images that are in the cloud database that matches with what is going on in production. And if they find something, then the system basically says that there is an error there. Again, the system is done, or the system is self-trained, so that if there is a new anomaly or an observation in the production line, the system can actually capture that and use it to self-learn, so that when that issue happens at a later point of time, they would be able to immediately catch it as a result of the self-trained algorithm that has been built into the machine learning model. So Instrumental Incorporated is the company that is using machine learning and deep learning very, very heavily in order to find issues in production lines of mobile phones, actually. Similarly, if you look at it, Hong Kong Polytechnic University, Professor Wong from this university has identified a tool, or has created a tool called Voice Eye, that again uses big data, machine learning, and deep learning. So he basically claims that if you were to find an issue or a defect in the fabric quality, it is very difficult for the human eye to catch it. So what they have done is they have taken help from people who are working in the production lines on textile industry, and they have took a lot of past data from there and loaded it into a machine learning model. And now this machine learning model has found about 40 fabric defects, which otherwise would have been missed by the human eye, and they have improved their precision levels significantly. So these are some examples of machine learning, deep learning, and artificial intelligence that is already happening in the testing space across other industries like textile, manufacturing, and others. Similarly, Internet of Things is another area where there is substantial level of artificial intelligence that is happening. Now, Audi, the car manufacturer, is using cognitive visual inspection powered by artificial intelligence to detect defects. It is very, very similar to what I just mentioned about Instrumental Incorporated. So if you are able to gather a lot of data of images, store them, and then compare them with what is happening in production and see if a car part is manufactured wrongly, then machine learning helps them to identify this. So Internet of Things as a technology is using, or it is relying on machine learning very, very substantially in order to detect defects early in the cycle. So the process basically is you have to collect a lot of data from the past in order to build your machine learning model. And even before you build your machine learning model, you will have to do a lot of activities on the data before it gets passed to the machine learning model. Otherwise, your predictions and accuracy can go wrong. So we will talk more about that in detail, but essentially wanted to leave the attendees with the idea that other industries are already using machine learning and data sciences, which are subsets of artificial intelligence, to find defects. And it is actually proved that there is early detection of defects using these technologies. And defects have been reduced up to defects have gone down by about 7 to 10% actually. And rather than spending human time on inspection, this effort or these technologies have helped them to improve the inspection time by about 80% actually. So it's extremely important to understand that other industries are already using this, and let us see how we can actually apply this to software testing in the subsequent slides. But before that, let's talk about data a little bit, which is the primary or the foundation of artificial intelligence. Now, before we talk about data in detail, there is one organization that could be a great example for applying defect detection using artificial intelligence. NASA is one of the early adopters of artificial intelligence in testing. And I'm not going to talk about rocket science here, literal rocket science here, but I'm going to talk about an approach that NASA is using today in order to do defect detection, because it is extremely important to understand the model they are using, because irrespective of what you do with respect to defect detection, whether it is in software testing or you do it in any other industry, the path to get there remains the same. The process to get there is the same actually. So if you are an organization trying to do defect detection using artificial intelligence, it's not going to happen overnight. It's extremely important to understand that you have to rely on a lot of data, and there is a process that you need to follow in order to get there. So NASA puts forth that process very clearly. So this is taken from one of the projects called JPL. And what happens here is, in the first step, NASA tries to identify a lot of past defects actually. In fact, as far as JPL goes, they have tried to identify about 40,000 failure records, which includes operational failure of software as well as non-software failures. Once they have collected this data, what they have done is they have done significant level of statistical analysis actually, which is trying to identify the different types of faults based on their behavior, and then try to see why these behaviors are happening, and then why some faults are easier to find than others, and things like that. So this has led to a classification. In software programming, there are a few terms that we use generally, but not in the common parlance. For example, we talk about defects, bugs, and terms like that. But there are some kind of terms like Bohr bugs, Mandel bugs, and things like that. These are not NASA's terms, but these are from the software engineering, computer science industry actually. So for example, a Bohr bug is something based on the Bohr atom model that we read in science. So a Bohr bug is something that is not very difficult to find, and it repeatedly happens, and there is a deterministic cause of failure actually. It is easy to identify why it is happening, and it is repeatedly happening. On the other hand, a Mandel bug is more in terms of it's difficult or it's complex to recreate that actually. It happens, but it's difficult to recreate that. So there are different kinds of these things that usually happens in the software industry. So if you look at computer science programming in detail, you can understand what a Bohr bug or a Mandel bug is. So as I said earlier, a Mandel bug kind of a thing is like a bug whose causes are so complex and it makes its behavior appear chaotic or even non-deterministic, which is more like flakiness, right? We are talking about flakiness a lot actually in software testing today. A lot of companies are trying to address the issue of flakiness. Mandel bugs are similar to flaky tests or flaky bugs actually. It can happen sometime due to an environment, but the next time it can pass actually. So what NASA is doing is it is trying to bucket this, or it is trying to classify these defects into a specific pattern, like Bohr bugs, Mandel bugs, and aging related. Now, in space shuttles and in any kind of space organization, it is very, very common that a space vehicle could be in orbit for a number of years actually, and as a result of that, there could be aging related bugs actually. So failure rate can increase with system being in runtime for long actually. So what NASA has done is, after they collected the data, they have tried to do some statistical analysis, and then they have tried to bucket these defects into different categories. And then they have tried to construct the machine learning algorithm. So what happens here is, by the time you construct the machine learning algorithm, there is a fair level of idea in terms of what we want to achieve, and then how we want to do defect prediction and defect detection actually, and improve your accuracy levels. So they have tried to do this classification before building the machine learning model, and the machine learning model has been fed with all these data sets of defects that they have already classified, identified, and everything, and that has resulted in improved identification of defect detection and failures. There are white papers, there are very, very detailed fault analysis white papers that are available from NASA online, and you can go ahead and read that. But the crux of this model, the process that we are talking about here, will apply to any industry when we talk about defect detection and prediction and accuracy improvement. So let's look at a little more in terms of data, because that's going to be the foundation of all the machine learning and artificial intelligence that you're going to do. So let's move ahead and look at what kind of data we are talking about here. Now, in a software testing scenario, there are, as I said earlier, we are already saying that companies are helping in test case generation. There are tools for test case optimization using machine learning. Test cases can be generated using automation. Sorry, it can be generated using artificial intelligence, or test automation can be done better using artificial intelligence. Defect detection accuracy and prediction can be made but better with artificial intelligence, and claims like that. But honestly, if you come to look at it, as we saw in the earlier slide in NASA, if you load 40,000 records from your past, then probably you are getting closer to prediction from a machine learning standpoint. But if you do not have any kind of past data, if you do not have anything to feed to the machine learning model, how is artificial intelligence even going to help you, right? So underlying machine intelligence or artificial intelligence efforts will completely fail or will be very biased if no quality data is fed to the machine learning engine. This is a very important point to understand, because software testing, when we say that we can use artificial intelligence in software testing without quality data being identified, how do you actually go and feed the machine learning engine? Because if you load something that is not relevant, if the data is not clean, if the data doesn't come with integrity, the machine learning model is going to fail, which means that you cannot do any kind of prediction or any kind of accuracy, right? So how do you identify quality data? Now, those are questions to think about. Where do you collect data? Suppose you want to do defect detection and software testing. Where do you collect data? Where do you collect your past defects? Do you collect them in production? Do you collect them in staging? Do you collect them in development environment? Where do you collect them? And how do you classify them? If there is a flakiness, if there is a defect that passes one time and fails one time, if there is a flakiness, how would you classify them? Like the way NASA has done in terms of Bohr bugs, Mandel bugs, and things like that. What kind of classification do you want to adopt for your model? Similarly, how do you build the right data model? How do you work with data scientists? How do you tell them what you want to do? What's your goal actually? If you're today at 60% defect detection, are you trying to go to 80%? In that case, what do you tell the data scientist? What kind of data do you provide them in order to build this model? These are very, very important questions to answer in the path, or in the in the journey towards using artificial intelligence in software testing, because it is the data that makes the difference. If you do not have solid data, if you do not have diverse data that can help, that can be cleansed, that can be reviewed, that can be confirmed for integrity, then you are not going to build a machine learning model. Because if the machine learning model is being fed with wrong data, it is going to produce very, very unpredictable, biased results. So unless and until you have a clean set of data, in this case past defects that are actually very, very useful in order to build this model, or past defects where we have seen flakiness, or what kind of defect that we want to see and things like that. Now for a UI, for a functional testing, for a UI testing part, you don't want to feed trivial defects into the system. So you want to rather look at crashes that are happening, how a code is causing crashes. So those kind of defects are what you want to feed into the machine learning model. Otherwise, what will happen if you feed about 30,000 past defects that are more in terms of UI issues, finding spelling errors or colors, fonts and things like that, then the machine learning software will also only predict those things. Not that they are bad, but as we all know, customers are willing to live with trivial issues, but they cannot handle, crashes and things like that. So in the journey towards identifying defects that can actually enhance the user experience, it is important to identify those defects that actually contribute to user experience failures so that they can be fed into the machine learning system. And as a result of that, we can have better prediction and accuracy. So it is very, very important to focus on the data here. Let's move on and look at a little more in terms of data and what's happening there, and what it takes to work within the team to produce this and all. As we said, data is the foundation of artificial intelligence. The more diverse the data, the better. And where is your data today? Now, we see companies are claiming that how to use your server logs in order to make betterment of your test cases using machine learning. We are exactly talking about the same, but where do you find them? Where do you get that information? So data can come for a machine learning model, or it can come for a artificial intelligence system from multiple ways. I'm talking about this exactly in the context of software testing. So you can get something from application logs that are running in production. You can get something from server logs that are running elsewhere. You can get something from your Splunk and Nagios in terms of monitoring alerts and things like that. You can get something from your test execution logs, anywhere actually. So you need to have knowledge and information in order to identify and collect this data. If you are not able to identify and collect this data, then your machine learning is not going to work. So you need to look for this data. Now, you can actually use machine learning to monitor data. You can look at specific bugs that are being caught in these systems like logs and everything. Absolutely. But we should know how to collect them, how to analyze them, clean them, review them, and make sure it is data with integrity before you feed it into the machine learning system, so that your prediction and accuracy can be improved. So from a software testing point of view, what is extremely important to notice, the QA testers will not be able to build a machine learning model. They are not going to be able to build a machine learning model. That is not their primary area of expertise. But where they can make a significant contribution is they can help data scientists understand what are the critical failures, what are the critical faults, what are the critical defects, or what are the critical crashes that has happened in the past, and where they can get this information. Now, that is where QA teams and subject matter experts in that specific domain can play a very, very vital role. So as you can see in the image, if there are more users who are knowledgeable in the system, like QA subject matter experts, they can contribute, or they can provide better data or more data actually. And once we cleanse, review and everything, this data that we get from these users can be used to build smarter machine learning algorithms, and that can actually go into better product design, better product quality and things like that. So it's a cycle basically. So that is the way data is going to work for you. So in a software testing context, we need to understand that it is extremely important to focus on the data. Here data would be defects, any learning, flaky tests, anything it could be, but whatever can contribute to better user experience and better accuracy in finding and detecting defects actually. So let's move on and see how better data can actually contribute to better artificial intelligence outcomes. As we saw earlier, AI, artificial intelligence, can be easily influenced. If you give wrong data, then you get wrong results basically. So you might want to look at how you want to train your data. Now, training the data is very important. So there is a set of steps that you do before you build your machine learning model, right? So for a QA engagement, you might want to look at getting training data first. A training data is something which is also called a supervised data. A supervised data. So there are three ways in which a machine learning algorithm can work. It can be a supervised data, it can be unsupervised data, or it can be retrained data basically. So what could happen is In unsupervised data, you just take some set of data and pass it, and then let the machine determine how the predictability can be improved. On the other hand, a supervised data is something which will be required much in the context of software testing, where a set of people can actually identify and give us that this is the training data that we need to use in order to train the machine learning algorithm. So we need to collect and classify supervised data specific to your problem. And then you need to do something called as feature transformation or pre-processing, where you process this, cleanse and everything. And then you need specialized expertise to build machine learning algorithms, which can come from your in-house teams or something like that. And then you need to train this data continuously in order to improve your algorithm, get better insights, and make accurate predictions and things like that. This is the sequence to build a machine learning model. Because if you do not use the sequence, then you will have a system that produces wrong outcomes actually. So if you are able to follow this process, then the output would be much better when it comes to machine learning. So in order to build something for software testing, you need to follow this process. And supervised data can come in from manual QA or from automated QA testers who can provide this information. And then data scientists can actually cleanse this information, make sure that is very the data is with a lot of integrity and things like that, and go from there. And then they can build their algorithms and then make sure that the algorithm can be self-trained, or it can get trained on itself based on future anomalies, future defects, future observations and things like that. So the past 3 slides, we have focused only on data, and that's where we thought we need to build awareness to testers and testing organizations and any software organization that is doing testing, that if you want to buy an external tool from the market and then feed your data, or ask or expect the tool to produce magic for you in terms of identifying test cases, or in terms of making your automation better, I don't think that's going to happen. So what would ideally happen is, you can actually rely on a tool, but even the tool needs to be customized very much to your context. Actually, the tool needs to understand what your data is and what your goal is. That way your outcomes can be much better. Otherwise, you will buy the tool, keep it with you, but you won't be able to apply it to your context. So if you plan to invest in artificial intelligence, if you have planned for artificial intelligence in software testing, it is extremely important to understand that you need the right set of data. You need data that is very specific to your context in order to get there. With that being said, let's move on and talk a little bit more again on the skills and how teams can come together and produce output that will be relevant to an organization's context. We spoke about this earlier. We spoke about how QA teams can actually contribute to better data, how QA teams can actually give inputs in the form of past test cases, defect history, production logs, and everything. Not just the QA teams, right? Today, we are talking about ops, we are talking about DevOps. So today, it's a collaborative testing model. So you have teams working on development, we have teams working on QA, and we have ops teams also. Each one of these teams will and they can contribute to the overall artificial intelligence effort. Ops teams can give inputs in terms of what kind of environments are actually causing failures, or where customers are actually finding issues. Customer support teams can give us inputs in terms of what kind of defects our customers see, and they can actually come in as inputs. QA teams can look at issues that are being found in their testing environment and other environments where they see issues and observations and things like that. And then developers can say what kind of issues they are seeing and things like that. Now, all of this is human. It's all human stuff. Now, this is a place where there is a human machine collaboration, and that's where we can do a lot more augmented intelligence rather than artificial intelligence. When I say augmented intelligence, trying to support human and getting support from them in order to build your data sciences or machine learning algorithm better, instead of relying on artificial intelligence completely. Because augmented intelligence can actually help in building a better system as opposed to pure artificial intelligence. Instead of trying to replace everything with machines, instead of trying to replace humans with humans with machines, if we can actually take support from humans, like in the context of software testing, we can actually build a much better artificial intelligence system. So as far as skills goes in building a machine learning model for defect detection and software testing, we need to understand that we need in-house teams like QAs, ops, and dev who can understand our data and the context to build the machine learning model and train that. And this is a collaborative effort between dev, ops, QA, data scientists, and everybody. And that is the only way to get a better model. Secondly, if you rely on external data and AI tools, it will help only when it is customized to your context. You can build a harness, you can build a test harness, or you can build a artificial intelligence based local harness for your testing system in order to in order to predict defects, which is something that will work for you. But if you are buying a tool from the market and trying to use it, I think that will be a challenging one actually. So instead of going for full-fledged artificial intelligence, it might be a good idea to use QA, Dev, Ops, and then include them with the data sciences team and produce something what we call as augmented intelligence that can actually lead to better outcomes. So if you are considering artificial intelligence in your organization, a better idea would be to make sure that you bring in your teams together and do more augmented intelligence rather than relying on pure artificial intelligence. So that's more on the skills and the kind of collaboration that you need within an organization to get the benefits out of artificial intelligence. Let's move on and look at an example of what we're talking about here. Now, Shuchi as a company has been helping some of the organizations in the areas of test case generation and identifying optimal test cases for organizations using machine learning. But as I said earlier, it is very, very contextual. It is very, very contextual to that organization. We have not built this overnight, but we have tried to do it over a period of time. So to look at an example, when you get a production issue today, naturally what happens is it's a fire in the organization. So the customer is already behind you, and engineering teams are trying to do their best to fix the issue, and very little time is given to QA in terms of running the tests for that fix and things like that. And most of the times QA say that I cannot guarantee much coverage for this particular fix because I didn't get enough time to test it. I don't think I've executed all the test cases that I need in order to do this and things like that. And this is an area where machine learning can actually come into play. And this is an area where we are doing some work for some organizations today. So what Shuchi has done for some organizations in this space today is we have tried to look at their context. We have worked with them for more than 1 to 2 years. So we have looked at their past defects. We have looked at their past errors and things like that, and also looked at what kind of issues have come from production and all that. Using that, we have built a machine learning model to predict test cases for ops and QA teams to run in a risk-based testing environment when a production issue happens actually. So Spider AI, as the tool is called, can be used to recommend optimal test cases for QA and DevOps team, and it uses a specific machine learning algorithm in order to identify this. So based on past records, past test cases, past defects, faults, and things like that, we have used the algorithm to churn optimal set of test cases when something happens in production, so that QA can get more confidence and ops teams can get more confidence to say, instead of doing a 60% or a 70% coverage, I will be able to give you a 80 or a 90 or a 95% coverage there. Of course, an 100% test coverage is something we all strive for, and that's not going to be easy. But we can very confidently say that as opposed to doing a 60 or a 70% coverage in production for this particular issue that came in yesterday from the customer, even though we have a time constraint, we will be able to actually do a 80 or a 90% coverage because I have a solution today that helps to recommend optimal test cases. I know what kind of tests I want to run in this scenario and things like that. So this is something very, very relevant to what we saw in the past. So the most important thing here is the past data. So the machine learning model in the case of Spider AI works with sparse data actually, and without that data we cannot produce the results that we are talking about. So the prediction and accuracy of the system works really well because the past data has been cleansed, it has been reviewed, and it has been provided by QAs within the system, and they have reviewed it and given it for consumption to the machine learning engine. So it is very important to understand that the past data is where most of your artificial intelligence effectiveness lies actually. So we have used that in order to build this, and we are able to guarantee better coverage, or testers are able to guarantee better test coverage using this model, and it has been working well for us. So again, the most important part of this webinar is to focus on data actually, because a lot of times we feel that we can buy a tool and get the maximum benefits out of it. You need to understand that buying a tool may not give us a lot of output unless and until the tool is customized to be used in our context. And that is what we should focus on. And that is the kind of artificial intelligence effort that will really produce outcomes. And in order to use that kind of an artificial intelligence effort, it is extremely important to understand that you have to rely on a lot of past data actually. And without past data, it will be very difficult to build a software defect detection model within your testing organization. Whether it is identifying test cases, or whether you are trying to identify defects, anything it could be. But it all depends to a large extent on your past data. Without that, it cannot happen. And as we have seen earlier, we are seeing this happening across industries. Whether you take hardware, any hardware batch processing system, or you take an Internet of Things company like car manufacturing, or you take, for that matter, textile manufacturing, you can very clearly see that these industries are using deep learning, neural networks, and everything only after the fundamental, activity of data collection is done. So if you actually come to think about it, it's like a hierarchy. If you want to build an artificial intelligence hierarchy of implementation, it all starts from data collection at the bottom. So data collection is the fundamental activity, and then it is followed by data cleansing, building your infrastructure pipeline and things like that. And then it goes into creating integrity, creating data with integrity, then deriving business intelligence or analytics out of it, and then finally applying your deep learning, neural learning, and everything. Now, without the first 2-3 steps, you cannot build this pyramid. So I just wanted to let all the attendees know that data would be the foundation for artificial intelligence in software testing. And data in the context of software testing refers to a lot of things: your past test cases, your logs, it could be anything for that matter. So if you are intending to build an artificial intelligence system for defect detection, I honestly request that you look at your past data, or you find a vendor who can actually help you, do this, who can actually build this pyramid that I just spoke about, who can come in, understand your defects, understand what has happened in your past, and then try to tell you what would be the roadmap to build this. And that is what, companies like Shuchi are doing today. So with that thought, we come to the end of this webinar. We have a Q&A session. I believe there are already questions coming in from the attendees here. So I would request Keerthi to read out the questions so that we can try and see if we can, handle a few of them. But otherwise, thank you so much for attending today. Let's look forward to the questions from the attendees. Keerthi, over to you.
Thanks, Vasu. We have a few questions coming in from attendees, and I've assigned them to you. You can take them up for discussion.
Okay. I'm just trying to see the questions actually. Can you read out, if you don't mind?
Yes, Vasu.
Okay, I think I'm able to see the questions. Yeah, thank you. I think I'll take care. Just one moment. So one of the questions that we see here is, okay, building a model, what does that mean actually? Okay, um, building a model means that the information that you use from the past is being trained in order to create a system. It's like in testing that we normally say there is an expected result and an actual result, right? So actual result is something that you find when you actually do the test, and then there is an expected result. So consider building a model as an expected result actually. So it is something that is lying out there, and it has taken a lot of past information, and we have built the model based on that. Now, that model will actually check your actual output or actual result and say if it's fine, or if there is any anomaly, it will be able to find it actually. So building a model, I would call it more like an expected result, but not literally or not exactly. But it is something similar to that. And building a model is what we spoke for such a long time, because model building is based on data. So building a model means that you are looking at past data, cleansing it, reviewing it, making sure it has integrity before you feed it into the machine learning. So a model is nothing but the machine learning system that took all this data and that tries to help you in making future predictions and things like that. That's what it means. The other question that I see is, so are artificial intelligence tool vendors not helpful? Well, there are different contexts in which whether you can say it's useful or not. Now, there are some companies that say that object recognition failures in test automation is something they can handle dynamically using artificial intelligence today. So this is a historical issue in test automation, right? Every time you go to an interview, the question that you get is, if you have object changes, what do you do with your scripts? So we are all used to it actually. So when you have that kind of a question, how do you handle it using artificial intelligence? Maybe there are some tool vendors who are doing it today. But to me, the question is, if you can do it today, why not 5 years before? Why suddenly now, right? Because object recognition as a challenge has been there for 10 years, 15 years now, ever since automation started. Why suddenly companies are claiming today that, we can use artificial intelligence for object recognition issues? We could have done it in 2005, we could have done it in 2002, we could have done it in 2010. So suddenly, last 3 years, 2 years, people are talking about how artificial intelligence can handle automation. So I really don't know whether it will work or not, because personally, I've not used it. But yeah, maybe organizations are actually doing it, and there is a way to do it actually. So you will have to, try it out for yourself. That's all I can say. The other question that I see is, test cases and artificial intelligence, what is the connection? Okay. As we just saw in the last slide, I believe it is still on the screen actually. Recommending an optimal set of test cases in a risk-based testing scenario is possible using machine learning and data sciences, but it takes a lot of past data. So for example, if you were to today go with a test case based, or what you call as a scripted testing approach, you are actually taking a set of test cases and doing the execution. Many times defects are found outside of the test cases. That's because we are actually not doing exploratory testing on the system to identify what kind of issues are actually being found, but we are relying on test cases that we write in a standard fashion and do it. Now, with respect to a tool like Spider AI that I just spoke about, it is possible that your past defects can become the input for your test cases actually. So what that means is, if you are able to design a system where you can take past test cases, past defects, log issues and everything, you can actually feed it to the machine learning engine, and then you can actually convert them as test cases and use them, which basically means that as opposed to going with the run-of-the-mill type of test cases, it is possible that you can actually use newer test cases that are more relevant to the customer, that are coming more from the customer environment actually. So that is what is the relevance between test cases and artificial intelligence. And here again, I'm using the term artificial intelligence a little loosely actually. Please understand that to me, or in general, to build a predictive system, to build something in a predictive fashion to improve accuracy, you are relying more on data sciences, machine learning, deep learning, neural network and other things, which are subsets of artificial intelligence, though all of these terms in general is being referred to as artificial intelligence. So let me make that clarification. So that's the relevance between test cases and machine intelligence. That is something I wanted to say. And the other question that we see is, what kind of defect prediction can we get here? How much of defect prediction can you guarantee? As I said earlier, a defect prediction cannot be guaranteed, but you can have a goal and move towards that actually. So you can say, my objective is to find 80% of defects before it gets into production, or 90% of defects, and then you might actually find only 60% today. If you are implementing a machine learning based model, then basically you can try and improve this accuracy over time because of the diverse data that you are getting actually, and it happens over time. It cannot happen overnight. So maybe when you start off, you might sometimes think that using manual testing or automated testing, I'm able to find defects better. Possible. But if you are waiting for 6 months for your model, if you're really training it well, if you're really able to give it enough inputs, then you can actually slowly start seeing improvements. The accuracy levels might improve actually, and things might be really better. So that is the way it works, but there is no guaranteed prediction or anything. So those are the questions I got, Kirti. Anything else on your plate? Anything else that you have that I missed here?
Yes, Vasu, we have a few more coming in. I'm assigning it to them as you're speaking now.
Okay. Can you go ahead with that?
Yes, Vasu. What technologies can you use for building machine learning models? That's one of the questions that just came.
Okay. Um, it actually depends, but to a large extent, it's Python which is used for machine learning today, and R, the programming language. But machine learning doesn't act just in terms of a programming language. You have other things for big data consumption like Apache Hadoop, Apache Mahout, and things like that. So it's a combination of technologies that can help you to do this, not just the programming language. But since you asked about technologies, I would say for big data consumption or for data consumption, you use Apache, Hadoop, Mahout, and other things. And in terms of the programming language itself, it might be easier to use Python and R for machine learning. Those are the technologies that are very much in use today.
Sure.
All right. Any other questions, or can we wrap up?
Yes, so we have another one.
Okay.
Can you give a real-time example how AI help automate a basic login use case?
Can you give a real-time example as to how AI help automate a
Automate.
real-time use case? Can you read that question again? Sorry.
Can you give a real-time example how AI help automate a basic login use case?
A real-time example for how AI can help. I really don't think you need AI to do this here. That's why AI is such a buzzword actually. Why do you need AI to automate a login case? To my knowledge, I think with the limited knowledge that I have, I don't really think you need artificial intelligence here. However, if you're force-fitting artificial intelligence for this scenario, one of the things you can do is you can take the login, you can build a data set out of it actually, and then you can try and see if the login has a specific administrator privilege, and you can say that if the users are coming in this model, they would be administrators. If users are like this, then they could be something different. So if you want to use a combination of diverse data for the login to make sure you are checking their access privileges for login, it is possible that you can use a data set that can be created with a diverse set of data, can be passed to the machine learning engine, and further on next time onwards, what the model can do is it can actually look at the user who is logging and say whether he is an administrator, or he's a user, or he's a network administrator, or he's a subscription user, or he's a controlled user, or he's a tester, or he's a developer, or he's an ops user. All that can be said, provided if there is enough information to do that. That's all I can think of, but I don't really think you need to force fit artificial intelligence into every scenario. I think we need to look at artificial intelligence as a solution for areas where it can solve problems rather than trying to apply it everywhere.
Sure. And one more question. For, for supervised learning, you need to have labeled data. I think you're suggesting that the QA results from previous sprints will be the source of labels on the data. Can that help identify defects in future sprints when new defects might be introduced?
That's a lot of questions actually. I'm not really sure if I can address everything. To a large extent, yes, supervised data is labeled data. You can actually get that and use it, but it's a very simplified answer to say it that way. I think we'll have to look into the context of what past data is, what kind of labeling it has, and then see how it can actually be considered supervised data or trained data for passing to the model actually. And in the context of software testing, it's a very different answer that we need to look at rather than just looking at it as data, because in this context we are talking about test cases, defects, and everything actually. So how do you label them, how do you make them a supervised is something that can happen only on the field. We can answer to this gentleman or lady whoever has raised this if we have the information in a separate thing, but broadly yes, but to a large extent it depends upon the context and depends upon the past data we are looking at and things like that.
Yeah, that is all for the questions part, Vasu.
All right. Thank you everyone for attending this today, and thanks for taking the opportunity to sit through this webinar. I hope it was useful. If you have any questions, please write to us. Visit our website and raise anything that you have. But once again, thank you all for waiting so long and for patiently listening to us. Thank you.